Oops, sorry. Roman, did you want to go ahead and introduce Nizar for us?
Oh, okay, yes, sure.
Thank you.
So hello, everyone. It's my pleasure to introduce our speaker today, Nizar Naitlho. He is a very active collaborator of a large research group, which includes people from Princeton Plasma Lab, General Atomics, and ITER site. So he works on the development of complex three-dimensional Lagrangian particle code and application of this code to the problem of injection of impurities in tokamaks, including ITER. So without further ado, Nizar, why don't you share the screen and the presentation?
Yeah, so hello everyone. Thank you all for attending the seminar today. My name is Nizar and I will be talking about Lagrangian particle model for 3D simulations of pellets and SPI fragments in tokamaks. This work was done under the supervision of my advisor, Professor Roman Samiliak, and in collaboration with my colleague, James, who's a PhD student in our research group, and Dr. Paul Parks, who's a scientist at General Atomics Lab. And as Professor Samiliak mentioned, the broader research team includes scientists from the Princeton Plasma Research Lab, General Atomics, and of course the ITER team. So here's the structure of my presentation today. I will start with an introduction, which includes an introduction to ITER and SPI and our Lagrangian particle code. I will then describe the near-field pellet physics models and the governing equations. I will present our main numerical results. And finally, I will give a brief summary of some of the current work in progress. So let's start with the introduction and the introduction to the ITER project. So ITER, which stands for the International Thermonuclear Experimental Reactor, is a large international program uniting 35 countries that will construct the world's largest tokamak in the south of France. So a tokamak is the leading candidate for a practical fusion reactor. Here on the right picture, we see a schematic of the tokamak with its plasma. The heart of a tokamak is a donut-shaped vacuum chamber. Inside the chamber, the goal is to hold the plasma stable for a sufficiently long time for fusion reactions to occur. The hot plasma is kept away from the machine walls by a magnetic field produced by two sets of coils, the poloidal coils, which go around the tokamak, and the toroidal coils, which loop across the chamber. And these contain the plasma horizontally and vertically, which prevents the plasma from cooling. The energy released from the reaction is then absorbed as heat by the walls, and it can be converted into electricity like a traditional power plant. So the ITER tokamak will have a major radius of around 6.2 meters. It is designed to produce a 10-fold return on energy, and it will demonstrate the feasibility of fusion technologies on a commercial scale. The assembly of the ITER machine began last July, July 2020, and the first plasma experiments are scheduled for December 2025, which will actually be the first time the machine is powered on. And finally, the first actual deuterium-tritium operations are scheduled for 2035. So one of the challenges facing ITER is to develop effective and reliable disruption mitigation techniques. Disruptions occur when an instability grows within the plasma, when the plasma operates beyond certain boundary conditions. And these instabilities lead to a loss of the magnetic confinement of the plasma. So here in this image at the bottom, we see disruptions in the form of these red patches along the vessel walls in the European jet tokamak. So these disruptions could occur, for example, when plasma current, plasma pressure, or density rises too high for a given magnetic field. And in fact, these red patches are areas where the plasma touches the vessel walls. So as a result of these disruptions, high amounts of energy contained within the plasma is dumped on the plasma-facing components, and these become damaged over time. Disruptions can also accelerate electrons, which are called runaway electrons, to very high energy, which creates a relativistic electron beam that can actually penetrate several millimeters into the vessel walls. So to fully maximize the use of the ITER machine, it is important to develop disruption mitigation techniques. The leading candidates for the ITER disruption mitigation system is the shattered pellet injection, or SPI system, which was designed at the Oak Ridge National Lab. So here in this bottom image, we see a design of SPI that is currently being tested on the D3D tokamak that is housed at General Atomics. So in this system, a large solid pellet is injected at high velocity into this bent guide tube, which is called the breaker tube. The pellet hits the wall of the tube and shatters into many pellet fragments. This stream of smaller fragments travels from the point of impact to the plasma boundary, where it enters the plasma and induces a thermal quench. And in this top image here, we can actually see a close-up view of the large number of pellet fragments that are leaving the breaker tube and entering the plasma. So even though the individual pellet fragments are rather small and a single one would ablate very quickly, the collection of a large number of fragments allows actually deep penetration into the machine. So the goal of this SPI technique is to disperse the energy of a disruption before it can concentrate its load on the vessel components, and it will also attempt to stop the worst case runaway electron beams. So the ablation of pellets and SPI fragments in tokamaks is intrinsically a multi-scale problem. The length scales can range from sub-millimeter size, which are, for example, the gradients of density near the pellet surface, to meter scale, which is the whole tokamak scale. There are also multiple time scales involved. And so in order to study SPI, we adopted a two-level approach. The study and simulation of the global tokamak scale model will be performed by two extended MHD codes, Nimrod and M3DC1. And these will resolve the tokamak plasma with realistic parameters over the required timescales. The limitation of these codes is that they cannot self-consistently compute the pellet ablation rate. Instead, the ablation rate is used as an input from an external model. Our group was tasked of studying and performing simulations of the local near-field pellet model, resolving the phase transition at the pellet surface and all the relevant physics processes in the vicinity of the SPI fragments, as well as computing self-consistently the pellet ablation rate. The goal of this two-level approach is that the global MHD codes and the local pellet codes will then be coupled and will exchange data files with the pellet code providing the pellet ablation rates to the tokamak codes. So I would like to talk in more detail about the various ablation processes inside the cloud for the near-field pellet model. The cold cryogenic pellet is injected at high velocity in the tokamak. The hot plasma electrons are streaming along magnetic field lines, and they hit the pellet surface, which causes rapid ablation. The pellet is then surrounded by a cold, dense, and neutral ablation cloud that forms and expands radially near the pellet. This cloud shields the pellet from the incoming electron heat flux, and it is the main factor controlling the ablation rate. The pellet material then heats up and undergoes atomic processes. So after it ionizes, the cloud expands along magnetic field lines, and it is constrained by the Lorentz force, which opposes the radial expansion of the cloud. Now, in addition to the parallel expansion along magnetic field lines, a grad-B drift moves the material across the magnetic field lines and establishes the pellet shielding length. And this grad-B drift is also an important factor for the ablation rate computation. In terms of the atomic processes inside the cloud, we use the Saha equation of state. We also use a kinetic model for the electron heat flux and the heat deposition at the pellet surface by the plasma electrons. This model depends on the density inside the cloud and an integral of density along magnetic field lines. And finally, for the phase transition at the pellet surface, we use appropriate boundary conditions.
Yeah, and Nizar, a quick question.
Yes.
What is the pellet actually made from?
Sorry, I couldn't hear you. So the pellets, we consider pellets from neon and deuterium, or we also consider hydrogen pellets as well. Yeah. So let me go on. So here I would like to briefly talk about the main theoretical and the computational models that have been developed for the pellet ablation problem. The main theoretical model is Paul Park's neutral gas shielding model developed in 1977. The neutral gas shielding model is a hydrodynamic model which was developed for hydrogen isotope pellets. It assumes a spherical symmetry for both the electron heating and the expansion of the ablation cloud. The states are computed from the 1D Euler's equations, the three equations of conservation of mass, energy, and momentum. It assumes a perfect gas in a spherically symmetric geometry with a volumetric heat source and three boundary conditions. And Parkes and Turnbull actually derived scaling laws for the ablation rate and computed the state variables at the sonic radius. Macaulay in 1994 also arrived at the same scaling laws by considering steady state hydrodynamic expansion of the cloud and using simple dimensional arguments. In terms of the computational models, Macaulay also developed a 2D localized code evolving the ablation cloud by solving the conservation equations. And he used artificial boundary conditions at the pellet surface. But the main shortcoming was that he did not include MHD effects. Ishizaki in 2004 developed a 2D hydrodynamic code CAP to study the dynamics of the hydrogenic pellets in spherically symmetric and axis symmetric models. Ishizaki's code treated the phase change at the pellet surface in a self-consistent manner without imposing the artificial boundary conditions, but he also did not include MHD effects. The first 2D MHD numerical model to rigorously and self-consistently include the interaction of the ionized flow with the magnetic field was developed by Professor Samiliak in 2007. His model was based on the interface tracking frontier pellet code, but at the time, he only considered deuterium pellets. More recently, my colleague, Nicolas Bousviel, extended this work to neon pellets and in addition developed novel numerical routines to track the ablation cloud, and he also implemented updated kinetic models for the electron heating. But the main shortcomings of all these theoretical and computational models is that spherical and cylindrical approximations are not applicable to multiple ablating pellets, which is relevant to SPI, and they also cannot resolve 3D effects such as the grad-B drift. So this motivated the development of our Lagrangian particle or LP code. The LP code is a highly adaptive, full 3D, massively parallel particle-based code with fast computing time. It performs 3D simulations of single neon and deuterium pellets, as well as many SPI fragments. It has optimal resolution and natural coupling with the global MHD codes Nimrod and M3DC1. We also have a 1D version of the code in Cartesian coordinates and spherically symmetric approximations. We performed simulations of the parallel expansion of ablation clouds over large distances and pellet ablation by runaway electrons with both the 3D and the 1D code, and we achieved good agreement between them. So here in this top image, we can see the capability of the LP code in tracking ablated material for long distances with the computational domain extending to 8 meters in length. But the LP code can also resolve a small domain in proximity to the pellet, where here the domain extends only 40 centimeters. So the Lagrangian particle code is based on the Lagrangian particle method, which was developed by Professor Samiliak and his PhD students at the time for hydrodynamic equations. For the sake of time of the presentation, I will not go over in detail on the Lagrangian particle method, but some of the key features is that each particle represents a Lagrangian fluid cell. It is highly adaptive to density changes. The LP method is a stable second order method with limiter, and it is easily generalizable to higher order methods. The main feature of the LP method is that it greatly improves the accuracy of the smooth particle hydrodynamics, or SPH, by replacing the SPH derivatives with generalized finite difference derivatives. Our Lagrangian particle code is written in C++ and parallelized using MPI. We have tested it on 4 40-core nodes on the Seawolf cluster here at Stony Brook University with more than 10 million particles. Now the LP code is based on constructing an octree data structure for particle distribution and searching neighbors for particles to build stencils for derivatives. So major octree algorithms significantly affect the code performance. In order to achieve better scalability and solve larger size problems, we linked the Lagrangian particle code with a powerful parallel octree library called pforest, which stands for Parallel Forest of K-trees. and the P-Force library was developed in the past within an ASCR-funded project of Omar Gattas. And I would just like to briefly mention that the development, verification using classical hydrodynamic problems, and scalability analysis have been performed for the current version of the LP code by my colleague, James. So one attractive feature of our LP code with regards to the pellet ablation problem is that the time step restriction is almost uniform and optimal in the computational domain. So here in this bottom image, I labeled the temperature scales of the different areas of the ablation cloud. The temperature at the pellet surface is around 50 Kelvin. The dense and neutral region near the pellet has a temperature of around 1 to 2 eV. The ionized material in the far field has a temperature between 5 to 10 eV. And finally, the background plasma has a temperature of 2000 eV. Now in LP, the high density gas that is close to the pellet is cold and slow with low velocity and sound speed. And so we represent it by small interparticle distances. But the high temperature and the high velocity and sound speed plasma in the far field has low density. And so it is represented by larger interparticle distances. So as a result, the time step in the LP code is about the same in both regions. We represent the background plasma implicitly by using ghost particles with plasma states. So this feature maintains the fast computing time of the LP code as compared, for example, to the frontier code. In our experience, 3D simulations with high resolution near the pellet surface achieved steady state in a few hours, while 2D frontier simulations took several days. So I will now go over the near field pellet physics models and the governing equations. So the main equations that govern the ablation cloud expansion are the inviscid compressible Euler equations with electromagnetic terms. The electron heat flux is represented by an external heat source minus delta Q, which is added to the energy equation. The Lorentz force is present through the J cross B term, and the energy balance from the Lorentz force is accounted for by the Joule's heating term. The current density is computed using Ohm's law. Now, in computing the current density, we made two approximations. First, we assume that the cloud is uniformly charged by the plasma electrons, which results in a constant value of the electric potential. And so the gradient of the potential is 0. And second, we assume that the magnetic field lines are constant and in the longitudinal x direction only. Finally, we have the equation of states, which closes the system of Euler equations. So in our work, we used two equations of states. For hydro simulations without MHD terms, we used the ideal gas equation of state, where gamma is the specific heat ratio. But for MHD simulations, we used a local thermodynamic equilibrium equation of state with atomic processes, which are multiple ionization in the case of neon and then dissociation and ionization in the case of the hydrogens. The local thermodynamic equilibrium is justified by high collision rates inside the cloud. And so the electron fraction Fe and the ion fractions Fm for all the ionized states can be computed by solving this coupled set of equations, which are called the Saha equations. And these Saha equations depend on values of temperature and density only. The Saha system, together with the conservation equations of mass and charge, is enough to determine these particle fractions. Once we obtain these fractions, the pressure and the specific internal energy are then easily computed from these formulas. Now, in terms of implementation of the Saha equation of states, the Saha system is a fully coupled system of nonlinear equations that is difficult to solve for each particle at every time step of our hydro code. So instead, what we did was we developed a Saha equation solver, and we created tabulated data of density and pressure. And during the runtime, we used table lookup and cubic spline interpolation, and this maintains the fast computing time of the LP code. The kinetic model for the electron heat flux that we use is the one developed by Paul Parks. Minus delta Q is the heat deposition rate per unit volume coming from the plasma electrons into the ablation cloud. And it is a function of U, which is the dimensionless opacity, where the plus and the minus refer to right-going and left-going electrons. The opacity itself is simply a line integral of the density along magnetic field lines in both directions. And I would like to note that at every point, the particles are hit by electrons from both sides. And so both the right integral and the left integral contribute to the same point. The important thing in terms of the implementation of this model is that the only challenging part is actually computing these line density integrals, because the particle discretization brings difficulty in computing these integrals. And so we developed an adaptive algorithm that I will now present. The question here is, how do we compute line integrals for highly non-uniform particle systems in the most accurate and efficient way? So suppose we start with a 3D distribution of Lagrangian particles in an SPI simulation, like this one shown here. The horizontal lines depict integral paths, and these are adaptively refined near each pellet fragment. So in the first step of our algorithms, we project all particles to the transverse plane, and we construct a quad tree data structure. We then adaptively refine the quad tree based on the number of particles in each quad tree cell. Now, each quad tree cell contains one path for the plasma density integral. And so in each cell, we redistribute Lagrangian particles to 3D using their longitudinal coordinate. We then sample computational nodes along the cells such that the distance between adjacent nodes is proportional to the local interparticle distance. Then we search particle neighbors for the computational nodes, and we compute weighted average density of the nodes. We numerically integrate the density along integral paths in both directions, since the heat flux comes from both sides. For the integration, we used the trapezoidal method, since this achieves second order accuracy. And as I mentioned, the LP method is overall second order accurate. Finally, we take the density integral value in each computational node, and we interpolate it back to the particles using a piecewise linear function. So we have the following boundary conditions at the pellet surface. The heat deposition on the surface of the pellets is given by the kinetic model. The temperature at the pellet surface is constant because the diffusion of heat is much slower comparing to the removal of the ablated material. The heat flux is completely used for the phase transition, which defines the mass flux, where epsilon s is the sublimation energy. The last missing boundary condition is provided by the Riemann wave curve, which is simply a solution of the hydro equations along characteristics drawn from the pellet surface into the computational domain. These equations give us a closed system, and we solve it at every time step to find the states at the pellet surface. Finally, we describe the grad-B drift model. So the schematic of the process is shown here on the left. The ablation material moves along magnetic field lines, and without the grad-B drift, this material would extend indefinitely, which would shield the pellet from the heat flux and completely stop the ablation process. The grad-B drift moves the end of the cloud across the magnetic field in the transverse direction, and the shielding length for the pellet is established self-consistently. The shielding length is defined as this, finite length of the pellet shadow that shields the pellet surface from the incoming heat flux. So the current model that we use is the one developed by Parks and Baillier. The Lagrangian derivative of the drift velocity is given by this formula, which depends on capital R, which is the major radius of the tokamak. P is the average pressure along magnetic field lines, rho is the average density, and M parallel is the Mach number of the flow parallel to the magnetic field. The last term in the equation is the drag associated with the generation of the alpha wave by the ablation cloud, where the VA is the alpha velocity. Now, in terms of the implementation, we again have to compute integrals of different quantities along magnetic field lines. So we use the same algorithm that I just described earlier. In this case, the right end computational node in each quad tree cell actually gives the correct integral value. And finally, the drift is applied only to ionized particles. The neutrals do not contribute to the integrals, and they don't experience any drift. So now I will present our main numerical results. So our first set of simulations were for benchmarking our LP code in resolving the pellet problem. We performed hydro simulations using spherically symmetric initial conditions and heat sources for single neon pellets. In this case, we ignored the MHD terms in the governing equations. The electron heat flux is a spherical heat flux, and the ablation cloud expands radially around the solid pellet in the absence of the Lorentz force, where the radius of the cloud is denoted by R. The line integral of density is now given by this simple integral. And here on the right, we have a 3D image of the full ablation cloud at steady state taken from one of our LP simulations. We used ideal gas equation of state with gamma equals to 5/3. And I also want to mention that we did not explicitly enforce the symmetry of the flow field. So we compared our numerical results with Paul's neutral gas shielding model. So this table above summarizes our results for the ablation rate of neon pellets. The pellet radius was varied from 2 millimeters to 5 millimeters. The background plasma temperature was changed from 2000 EV to 5000 EV. In this third column, we have the ablation rate as predicted by the NGS model. In the fourth column, we have the ablation rate computed by our Lagrangian particle code. And finally, I've listed the error difference between the two ablation rates. So as we can see, the agreement is very good. We achieved less than 2% error in all cases. And considering again that the simulations were performed in 3D without explicitly enforcing the spherical symmetry, we achieved a very good agreement with the theory. So next we moved on to MHD simulations. So as I mentioned before, as the ablation material heats up and ionizes, it propagates along magnetic field lines. The grad-B drift establishes the finite shielding length for the pellet. But before performing full simulations with grad-B drift, we wanted to verify our LP code in resolving MHD problems. And so we performed code comparison work with the 2D axisymmetric frontier code. Now, since Frontier cannot resolve 3D effects such as the grad-B drift, in order to avoid this cloud extending indefinitely and completely stopping the ablation process, we imposed a fixed shielding length, which we theoretically estimated to be 16 centimeters, which in this case is the half cloud length. And all Frontier data was provided to us courtesy of my colleague, Nicolas Bousviel. So this slide summarizes the results of our code comparison work. On the left tables, we have values of the ablation rates from LP and Frontier for 2 millimeter neon pellets in magnetic fields ranging from 2 Tesla to 6 Tesla. And on the right, we have the corresponding values for deuterium, 2 millimeter deuterium pellets, where the magnetic field was changed from 1.6 Tesla to 6 Tesla. We plotted our results here. The blue dots are the ablation rates for neon pellets obtained by the Lagrangian particle code. The blue X's are the values from Frontier, and the blue line is an analytical fit using both data points. And we plotted the same thing in red here for deuterium. So as we can see by comparing the dots and the X's for both neon and deuterium, we have excellent agreement with Frontier. The overall behavior is the same, and both codes predict a very strong reduction of the ablation rate with higher magnetic field strength. The reduction factors from both codes are also close for both neon and for deuterium pellets. So to explain the reason for this behavior and this strong reduction of the ablation rate in higher magnetic field, I would like to go back to the previous slide briefly. So here in this top image, we have a 2D temperature distribution from LP simulations of a neon pellet. In the top, the magnetic field strength was 2 Tesla, and in the bottom, the magnetic field strength was 6 Tesla. So as the ablation material, without grad-B drift, the cloud is completely confined to this narrow ablation channel by the Lorentz force. With the increase of the magnetic field, the Lorentz force actually becomes stronger, and the ablation channel narrows even further. And we can actually see this by comparing the radius of the channel, where in 2 Tesla field, the radius of the channel was 1.5 centimeters, and in 6 Tesla field, this went down to 1 centimeter. So this condensing or squeezing of the cloud increases the density in the cloud, which provides more screening to the pellet from the electron heat flux. This decreases the amount of energy that actually reaches the pellet surface. And so as a result, the ablation rate goes down in the higher magnetic field. So after performing the verification and the code comparison work, we were ready to perform MHD simulations with grad-B drift. So in this case, in addition to the parallel flow, as I mentioned, both ends of the ablation cloud are displaced beyond the main cloud shadow. We have labeled what we mean by the shielding length. So the plasma electrons are hitting the cloud in the longitudinal direction from both sides. And this finite length of the pellet shadow, which shields the pellet surface from the incoming heat flux, is what we call the shielding length. We implemented the grad-B drift model in our LP code, and we performed simulations of 2mm neon and deuterium pellets, where the tokamak major radius was set to 1.6 meters, which is the D3D tokamak radius. One brief comment about the alpha drag. Our results show that the alpha wave drag is negligible for both neon and deuterium pellets in simulations, where the goal is to compute the ablation rate. If, however, we are interested in the parallel and transverse expansion of the ablation flow at large length scales, then this alpha wave drag becomes an important factor. So here we have a summary of the results of our simulations of the ablation of deuterium pellets with grad-B drift effect. The first column of the table contains the magnetic field strength. The second column lists the shielding length. And finally, the third column lists the ablation rate. In the plot over here on the right, the ablation rates from the table are marked by the red dots along with the red line, which is an analytical fit. And in blue, I have the ablation rates that I showed before for the case with no grad-B drift, where we imposed the fixed shielding length. So the first thing we immediately notice is that the reduction of the ablation rate in higher magnetic field is much weaker compared to the fixed shielding length. The ablation rates are close in 1.6 Tesla fields, but these values deviate from each other as we move closer to 6 Tesla field. The second point is that the shielding length decreases with higher magnetic field. Here we have a summary of the results of neon pellets with grad-B drift effect. Again, we have the same plot on the left, which compares the ablation rates from grad-B drift simulations in red to those obtained with a fixed shielding length in blue. And again, we observe that the reduction of the ablation rates with grad-B drift is much weaker comparing to the fixed shielding length case. So the question is, why do we observe such behavior? So the first reason comes from the shielding lengths. Since the shielding lengths decrease with the increase in magnetic field, this reduces the pellet shielding and increases the amount of energy that reaches the pellet surface. But this alone cannot account for the large difference in ablation rates that we observe in 6 Tesla field. The main reason for this effect is that the overall properties of the ablation cloud actually change. So remember, without the grad-B drift, the cloud was confined to a narrow channel by the Lorentz force, and the radius of the channel decreased with a higher magnetic field. With the grad-B drift, we do not have such a confinement, as we can see in these images on the top, where on the left, the magnetic field was 2 Tesla, and on the right, the magnetic field was 6 Tesla. In this case, the ablated material drifts across the magnetic field lines, and it makes the shielding length effect less sensitive to the change in magnetic field. We can actually see this more quantitatively in this next slide, which compares the neon cloud density for 2 Tesla field in red and 6 Tesla, 2 Tesla field in blue and 6 Tesla field in red. In the left plot, we plotted densities for fixed shielding length simulations, and in the right plot, we had the densities where the shielding length was established by the grad-B drift. Now, by comparing the blue lines, we see that these are actually close, and the density in 2 Tesla field is approximately the same in both simulations. And we actually observed this in the ablation rates, where we obtained 23.3 grams per second for the fixed shielding length case and 24 grams per second for the grad-B drift case. With the increase in magnetic field, the density is significantly higher in the fixed shielding length case, especially in the far field where the density is almost constant. Remember that this is the region where intense ionization takes place. And so in the grad-B drift case, where the drift is applied to the ionized particles, this ionized material drifts by the grad-B force, and the density in the far field quickly falls down. So this lower density leads to higher ablation rate in 6 Tesla field, where we obtained 10.4 grams per second for the fixed shielding length case and 18.2 grams per second in the grad-B drift case. So this is why I mentioned before that the grad-B drift is important in computing the ablation rate, since it completely changed the properties of the ablation cloud. So up to this point, the pellet was treated as a fixed object that ablated indefinitely. But in order to assess the viability of SPI, we need to have some knowledge of the lifetime of pellets in the plasma. We are currently studying scaling laws, which relate the ablation rate to plasma parameters and plasma radius. In particular, the ablation rate is proportional to electron temperature to the power 5/3, electron density 1/3, and pellet radius 4/3. Now, the pellet radius changes in time according to the mass conservation relation. So suppose we are given some ablation rate G0 for some plasma parameters and some initial pellet radius RP0. We can compute the ablation rate for any pellet radius from G0 and RP0 from the scaling law. Substituting this expression for G in the first equation above, we get an ordinary differential equation that we can solve to find the pellet radius as a function of time, and by extension, the ablation rate as a function of time. So one of our goals is to establish a scaling law for pellet ablation in magnetic fields with grad-B drift. We first verified the dependence of the ablation rate on the pellet radius by assuming the plasma parameters and magnetic field constant. Now, the LP code computes the ablation rate directly at every time step. And so we can actually solve the first equation on the previous slide at every time step to get the pellet radius at time step n+1 from the pellet radius at time step n and the ablation rate at time step n. So we performed simulations of neon pellets in 2 Tesla field for starting with developed cloud, where the pellet radius was 2 millimeters. And the ablation rate of the developed cloud was 25.1 grams per second. And we set rho 0 to be the mass density of frozen neon. So these bottom plots summarize our results. We compared results from LP given by the blue line to the analytic solution and the scaling law given by the red lines. On the left plot, we plotted the pellet radius versus time. And on the right plot, we plotted the ablation rate versus time. So as we can see, we have a very good agreement between our LP results and the analytic solution over long timescales for both the pellet radius and the ablation rate. And so we concluded that the scaling law for spherical symmetry holds for the pellet radius in magnetic field with grad-B drift. We have now moved on to investigating the dependence of the ablation rate to the plasma temperature. So these were our main numerical results, and now I will to give a brief summary of some of the work in progress. So after performing extensive studies of single neon and deuterium pellets, and naturally the next step is to perform SPI simulations with a large number of fragments. We want to use a typical setup of experiments performed in the D3D tokamak. We expect the large solid pellet to be shattered into approximately 250 fragments. Using information from the experiments, we were able to find that the average radius of a single fragment will be 0.066 centimeters. These fragments are expected to be more or less uniformly distributed in this plume of approximately 30 centimeters in length and 30 centimeters in diameter. So this gives us an average distance between fragments of 4 to 5 centimeters. So we have already performed many SPI simulations of a number of fragments ranging between 2 to 40 fragments. We started by simulating a subset of the whole plume. The subset was fully resolved in the longitudinal direction, which is the direction of the magnetic field, and in the transverse direction, which is the direction of the grad-B drift. In the z direction, the slice was approximately 5 centimeters, and so it contained anywhere between 10 to 50 fragments. In this example on the top right, we simulated the ablation rate, the ablation of 10 fragments with a pellet radius of 0.066 centimeters. We observed that fragments that partially screen each other, either directly by being on the same magnetic field line or through the grad-B drift, interact, and this affected the ablation rate. In this bottom figure, I just wanted to show again the adaptive selection of integration lines for the heating and the grad-B drift models. So after projecting all the particles and fragments into the transverse plane, we constructed a quad-tree data structure for all particles, and the color map shows the different quad-tree levels. In low density areas, we have these large cells shown in blue, but near the different pellet fragments, we have highly refined cell. And each cell shown in the figure contains one integration line, even these small red cells shown here on the right. So this demonstrates the adaptivity of our integral algorithm. We have also started investigating the interaction between pellet fragments and runaway electrons that are generated during tokamak disruptions. In the runaway regime, the plasma is cold. The temperature ranges only from 2 to 20 eV as compared to 2000 eV, which is 2000 eV plasma temperature that we considered before. And so the only heating is the volumetric heating by runaway electrons. The runaway electron beam had an energy of about 20 MeV, and we considered different densities for the runaway electron beam. We performed simulations of neon and deuterium pellets, and we compared our results with other simulations, such as the ones made by Kiramov in a nuclear fusion paper published recently. In the case of deuterium pellets shown here at the bottom, we observed some hydro instabilities develop, especially at later time at 400 and 500 microseconds at the edge of the cloud. And right now we are currently working on hydrogen SPI fragments ablated by runaway electrons using ITER parameters of the runaway beam, the background plasma, and the SPI fragments that were recently provided to us. Finally, we are also working on the multi-scale coupling with the tokamak codes Nimrod and M3DC1. The direct coupling is extremely difficult and even inefficient due to very different geometries and timescales. So in a discussion with general atomic scientists, we proposed that the grad-B drift provides a natural way of performing the coupling. The idea is that the particles which drift beyond the main cloud do not provide shielding to the pellet anymore, and hence they don't affect the computation of the ablation rate. So we propose to delete these particles from the LP code and copy them to the global codes, where here we have a Nimrod simulation domain showing ablated material obtained from our Lagrangian particle code, courtesy of our colleague Charles Kim at General Atomics. In the very near future, experiments are scheduled on the D3D tokamak with neon pellets to verify all the results of all the work I presented today. But recently, M3DC1 performed a 2D simulation of a 1 millimeter neon pellet with parameters from one of these experiments. M3DC1 provided us with data files containing plasma states, plasma density, temperature, and magnetic field at every 50 microseconds. So we performed LP simulations using these plasma parameters, and we compared ablation rates. So in this plot at the top, the ablation rate obtained by the LP code is given in blue, and the ablation rate computed by M3DC1 using the external source term is given by the red curve. So as we can see, the ablation rate from our LP code is in the range of the ablation rate computed by M3DC1. But the idea is that M3DC1 will pick up our ablation rates along the pellet trajectory and send us new plasma states. And we will then compute the ablation rate again, and we will go back and forth until we achieve some convergence. So the work I described today, which includes the verification of the LP code, the code comparison with Frontier, and the grad-B drift results, was recently published in Nuclear Fusion Journal. We have also presented our work in several presentations and poster presentations recently in various conferences. And here is a list of references to all the theoretical and computational models of the pellet ablation problem that I described at the beginning of the presentation. And I've also listed a reference for the Lagrangian Particle Method and the P4est library. So thank you all for listening to my talk, and I'll be happy to take questions from the audience.
Nizar, many thanks. A quick round of applause from everyone. I guess you get the golden hand clap from some people, so fantastic.
Thank you. Thank you.
So let me jump in with a quick question. So,
Sure.
I mean, the really impressive calculations. I mean, you're bringing so many things together here. And that's also part of the challenge, isn't it? You've got the Lagrangian particle method that's got sort of like some rigorous understanding of convergence and so on. And you've got the cubic interpolation used for the one of the underlying models. You've got the in your time integrals, you've got the various the trapezoidal integration followed by the linear interpolation back down onto your particles. And so how do you piece together all of this into demonstrating you converged?
Convergence usually was done by, so in our simulations, we performed a steady state computation of the ablation rate. So this means we start with, let me go back to one of the, we start with a cryogenic pellet, 2 millimeter spherical ball, and we ablate it using the plasma parameters. And we do this until we achieve the steady state where the ablation rate over time reaches a constant value. So convergence in this case would be changing, for example, the resolution that we use, which is for example, the number of particles that we use in our simulations, and achieving the same steady state ablation rate by changing the resolution.
Okay, and you've got multiple knobs, so presumably you have to tweak each knob and make sure each one is behaving satisfactorily.
Yes. Also, the various models that I described, for example, the density integral, we performed standalone verification of this density integral. For example, we started with like a cylindrical cloud with a Gaussian distribution, okay, and then great. we applied our density integral algorithm, and then we compared it with analytic solution, which is just the integral of a Gaussian function. So all these smaller numerical algorithms that we developed were tested and verified in standalone problems. But in terms of the pellet problem, our main thing is the steady state ablation rate computation, and so we have to achieve the same ablation rate by changing different factors and the resolution.
Okay, very good, thank you.
Yes, and we also achieve good agreement with experimental measurements for ITER.
Okay. So the combination of validation and verification. Okay.
As it's supposed to be computational science.
Exactly. Reality is the ultimate determination of correctness.
So I have a quick question, if that's okay.
Yes. Sure.
Very nice work. Again, it sounds like you have working models for things like the pellet ablation and stuff like that. What does your work say about the broader project? I mean, obviously, if you have a good working model for part of it, that gives you more confidence. But is there anything in particular that the broader project of the ITER can draw from your work?
So as I mentioned before, actually the simulation of the plasma in the tokamak will be resolved by the Nimrod and M3DC1. The limitation is that they cannot self-consistently compute the pellet ablation rate. So that's where our work comes from, and where we resolve all the physics processes in the vicinity of the different fragments, and we provide the ablation rate to the tokamak models. Of course, the ablation rate determines the lifetime of the pellet inside the tokamak. So in order to assess the viability of this SPI in dealing with plasma disruptions, they need to know how the pellet ablates, how the pellet radius changes over time, and they need our pellet ablation rate in order to perform accurate measurements.
So is it fair to say that they'll build subgrid scale models on your work? Is that a way to put it, or?
Yeah, you can say that these are subgrid scale models. That there'll be various levels of subgrid scale models. The basic one would be just modification of analytic scaling laws by using our simulation data.
Okay, so something like that would be a timescale for the pellet to live, or?
Ablation rate based on the plasma parameters.
Yes.
So we are working on the computation of numerical data sets of the pellet ablation rates for various plasma parameters. And of course, we would like to reduce the dimensionality of this parameter space as much as possible. So what Nizar did not mention is that all practical tokamaks, including ITER, and of course all previous machines like D3D and JET, they approximately have the constant ratio of the magnetic field in Tesla to the tokamak major radius in meters. So this is one constraint which allows us to reduce the dimensionality of the parameter space a little bit. But other than that, we have to just compute ablation rates at various plasma temperatures and densities. So this is one way. And more sophisticated way is to directly get data from our codes into tokamak codes.
Yeah, so Professor is talking about this, which I didn't mention, which is that for most machines, the ratio of the magnetic field to the major radius is approximately 1, including the ITER machine. And so in the future, we will perform simulations with this constraint of setting the magnetic field divided by the major radius equal to 1. And we have actually already done that for neon and deuterium pellets for magnetic field ranging from 1 Tesla to 6 Tesla. And here on the left, we have the ablation rates, and on the right, we have the different shielding lengths.
Right, but the value of the code is not only in building a subgrid model to tokamak MHD codes, because many problems in ITER cannot be performed by tokamak MHD codes because they cannot deal with cold stuff. So for instance, if you inject into cold plasma SPI and ablate this SPI by runaway beams, then the ablated material remains quite cold. And tokamak codes cannot deal with cold and almost neutral material. So our approach would provide long-scale expansion of this ablated material in the entire ITER. And so we just had 2 meetings with ITER people over the couple of last days. And so we continue some extra work in that direction.
Sounds very good. Robert, you're muted, I think.
Sorry about that. I put a link to the ITER project in the chat window, and
Yes.
the banner. If you click on the banner and just right arrow, it'll cycle through the videos shown in the banner. One of them is entitled "Amazing Machines," and it actually shows the pellet injection process. It's probably the fuel pellet rather than this particular pellet,
Right.
but
Yeah.
it's an amazing machine, really, and it's really exciting to see people here working on this project. Just incredible.
So that animation is an artwork. It's been on the ITER page for a long time. But in fact, they did this very well. It's quite close to our Lagrangian particle simulations.
Okay, very good. Yeah, I wouldn't mind their art budget. I'm sure their art budget is bigger than our annual budget for everything. Yeah.
And these are in the chat. Oliver wants to know that, let's see, he said, I've heard of spherical tokamaks. Do you know if those are better?
Spherical tokamaks.
Instead of toroidal.
Toroidal, yeah.
Well, look, there is no very big and serious spheromech nowadays. So people pay big attention to stellarators, of course. There is W7, Wendelstein 7, working in the Max Planck Institute in Germany. So this is new and very sophisticated machine. And the main advantage of stellarator is that there are no plasma disruptions in stellarators.
Right.
So what we do is totally irrelevant to stellarators. But our work is also important for the fueling of tokamaks or stellarators, because if you burn plasma, then you need to provide new fuel material. So in terms of fueling, both ITER and stellarator need injection of new fuel in the form of frozen deuterium tritium pellets. But as for plasma disruptions, stellarators are excellent. They do not have plasma disruptions. I mean, violent plasma disruptions, damaging the walls. So I think community talks about advantages and disadvantages of these two projects. And of course, there are some ideas about building very compact, small tokamaks. But I wouldn't be qualified to describe, the future of these compact tokamaks projects.
Okay, very good. So I guess we should wrap things up. We're running out of time. And so, Nizar, thank you very much again. Truly exciting and very engaging talk. Thank you.
Thank you all for attending today.
Thank you. Right.